John Felix Kumar to invite the speakers. Over to you, sir.
Good evening. As head of the Department of Metallurgical and Materials Engineering, Jyoti College of Engineering, Kanjirapalli, Kerala, I welcome you all for the 6th webinar of National Webinar Series on Prospects and Career Opportunities in Metallurgical and Materials Engineering, the way forward, through this online Zoom platform. The National Webinar Series consists of 8 talks from eminent scientists and professors from reputed institutions and organizations on a weekly basis. On the webinar series, the 6th webinar, today it's a very special moment for all of us, and we are more privileged to have Professor K. Narasimhan and Professor Parag Bhargava as resource persons. I would like to take the opportunity to introduce about the professors. Professor Narasimhan is currently head of the Department of Metallurgical Engineering and Materials Science, Indian Institute of Technology, Bombay. Professor Narasimhan has more than hundreds of publications in peer-reviewed journals, including the prestigious Scripta Materialia. His areas of interest are sheet metal forming, superplasticity, modeling and simulation. And Professor Parag Bhargava is currently professor in the same department, and his research interests are synthesis of weakly agglomerated nanoparticles, fabrication of ceramics for prosthodontic applications, sensitized solar cells, high temperature foam and fibre-based thermal insulation, glasses and glass ceramics. Moreover, Professor Bhargava has 5 patents to his credentials. We extend our wholehearted welcome and sincere thanks to professors for accepting our invitation to share their rich experience to the student community, even though they are busy with their schedule. And today's session is planned to be more interactive, and participants are requested to figure out questions related to the focus of subject only. Now I invite Professor K. Narasimhan and Professor Parag Bhargava to deliver the talk on scope and opportunities in metallurgical and materials engineering for an engineering aspirant. I welcome you, sirs.
Thank you so much. Good evening to you all, and thank you, Professor John Kumar, as well as your Department of Metallurgical Materials Engineering, Jyoti College of Engineering, for this great opportunity for myself and my colleague Professor Bhargava to be amongst you here, and to I would say more like having a chit chat and learning from each other. So this is the platform that you have provided us, and we are really very thankful and appreciative of this opportunity. So before we begin, I first would like to relate back to my very first visit I had a few years back to this college. And it was really a very exciting experience for me to come to your college and, give some talks on sheet metal forming. And that experience was very wonderful. I found the ecosystem there was excellent. The students were really very, very motivated. So I can never forget that experience, and certainly, I'll look for another equivalent opportunity, of course, post-COVID, to be able to visit your college again. So with this backdrop, let us get to our program. As it was mentioned, we would like to keep it as interactive as possible. So if you would like to ask us anything at any point of time, just raise your hand. I believe you can do that digitally. So I am not an expert in any of this high-tech stuff, but I believe that you can raise your hand digitally, and and then the organizers can allow you to ask your question. So it could be during, I am not going to make a very structured PPT kind of a talk. I'm just going to be blabbering like this in front of you. So I will have also some questions for you, and you can also have any queries. And of course, there is no guarantee that I'll have an answer, but that's how we learn from each other. So let's keep it in a nice interactive fashion. Since we were told that a good set of the audience is from schools, I hope that is correct. Yeah.
Yes, sir. We have higher secondary students also.
Yeah, there are going to be a significant number of school students.
Actually, we have right now 172 participants. So most of the participants from higher secondary.
Okay.
Plus
so
students, yeah.
School students, right?
The
yeah.
students.
So I would like to have any of them, kind of share their opinion on what they think is metallurgical engineering and materials science. If anybody would like to, we all form our opinions, perspectives, so on and so forth. So I would like to hear from maybe at least a couple of them what they think is this, metallurgical and materials engineering. So if anybody would like to comment, we would like to hear that. Is there anybody who would like to respond to this, please? In your opinion, in your thinking, what do you think is metallurgical engineering materials?
Study of metals, study of structure of the metals and its behavior.
Excuse me, the participant, please turn on your video so that professors can see you also.
The study of metals, its structure and properties and behavior is known as metallurgy, sir.
Okay, very nice, very nice. So that's a good perspective. Anybody else would like to comment? And please also, you may introduce yourself if you wish, so that we get a better feel for who you are and all that, right?
My name is
I'm not able to see the person. So I think what you have to do is you have to say speaker view or something like that, so that
we are having a preview, sir.
Yeah, I can see, yeah.
My name is Jahnavi, sir. I am from the JNTU College of Engineering, Vijayanagaram, sir.
Okay, then you are an expert. Then I should stop. I should let you speak. Right?
No, sir. I am not an expert student, sir. I am an average student, sir.
Okay, very nice. Thanks for your, your comment. Would anybody else?
Thank you,
maybe. Thank you. At least we can take one or two more if anybody would like to, share. Especially school children. If there are school people, I would like to hear from them. Yeah, don't post it, just talk. I think somebody is posting, I can't follow chat and hear. No, for me, if one of the sensory organ work, I can't see, hear, do everything parallel. So
we have engineering aspirants also, so they can also send, right?
Yeah, there is some Janvi Vedala who wants to maybe share something. Janvi.
Hello.
Sir, I'm here, sir.
Yeah, go ahead.
I think she already spoke, no?
Yeah. Oh, is she the one who spoke? Okay, then
probably.
Swapna is raised now. So maybe we'll take one more view, Swapna, and then we can go on. Swapna, would you like to say something?
Good evening, sir. Good evening.
Yeah, good evening. Please go.
Now you can turn on the video camera.
Good evening, sir.
Okay, I think maybe she has a bandwidth issue. That's fine. So at least we got one feedback.
Hello.
Yeah.
Hello, sir. Hello, sir. Myself, Mitesh Lad.
Yeah.
Actually, I am working in a GE, General Electric. Okay, and I did my master's in welding technology from MS University of Vadodara. Okay. What I understood about the metallurgy is in world, in planet, everything is made of with some defined structures, defined way. Okay, and we have to understand, or we have to utilize for engineering purpose to understand their behavior. Okay.
Good. Very nice. Very nice. Thank you for that. Yeah. So I think we got some impression, and I'm sure, many of you must be churning in your mind, how, you can think about this. Probably we can continue and we can come back to that. So let me now, if you permit, we'll go ahead with some of the thought process I have for, this session. So I would like to, break it down into, before my colleague, Prof. Parag Bhargava, gives his insight. I want to talk a little bit about the significance of this broad field of metallurgical engineering and materials engineering. And what does it really mean? What is this? Of course, that's what we got some few comments, like what does metallurgical and materials engineering mean? So we'll try to develop on it a little bit. And I also would like to emphasize the interdisciplinary nature of this broad area. So that I would like to touch upon a little bit on that. And of course, finally, we can wrap up with commenting on the career opportunity. So that we will take it up after my colleague, Professor Parag Bhargava, has given his insight. So this is what, in a nutshell, we'll try to do. Now, looking at, the significance, can you all hear me? I'm assuming you can all hear me. Am I audible?
Yes, sir. Audible, sir.
Some voice, something saying.
Yeah, audible, sir.
Maybe I'll have to keep it on my lap.
It's audible, sir. It's audible. If you come across with any technical issue, you can comment in the box below.
Okay, no, somebody
can come in the box.
So I'm
We'll fix it
closer to me. Okay. Yeah. So, and somebody saying something. Okay. So let's look at the significance and importance of our field, the metallurgical and materials engineering. So if you look at the civilization, I mean, this is like nothing new I'm telling, but if you look at it, it is linked to materials. So we talk about Stone Age, Iron Age, Copper Age, whatever. You heard of all, this kind of an age. So this clearly tells us that the material or metals that we are talking about is extremely important, and it is, linked to the civilization itself. So you can very clearly appreciate straight away the importance of metals, materials. If the civilization itself gets associated with this kind of the material development, we can appreciate that. Of course, this development is continuous and it's happening even as we speak today. Okay. So if you look at any kind of a major breakthrough or technology development that takes place, they are all material dependent. See, all of us in today's world, especially in this pandemic, where we really can't, meet physically, all of us are using our smartphone every day, right? So if you think of smartphone, you can think of the kind of material development that has to have taken place in order for us to have that in our hand, right? So in that way, anything we make use of, you will find that it is a material world, right? Anything. You are driving your car. So what is a car? Car has a whole bunch of material and components made out of different types of materials, right? So that is the real importance. It is going to be part of our every walk of life, right? So the material development, manufacturing, will have a huge, big impact in our day-to-day life. And that, really brings home the importance and significance of, metallurgy and materials engineering. So this, I just want to give you, just this kind of a introductory remark on the importance and significance. So if you are thinking, especially this is for, the school children who are in your maybe 11th or 12th, if you're thinking about metals, materials, you're thinking right. You're in the right direction and you really have plenty of opportunities. And towards the end of our interaction session, we will also talk about the, the career opportunities. But if you're thinking about it, this is really a very good, area to be in, right? So now let's just come back to understanding what is this metallurgical engineering and materials engineering. This is where the couple of comments we heard by our participants are also very relevant. They really were, in the right direction. They made the right comments. So essentially, what are we doing in metallurgical and materials engineering? So we are dealing with development and application of wide range of materials. This is one way of trying to appreciate and understand, what is this metallurgical and materials engineering, right? So it involves not only development of wide range of materials, but also the associated manufacturing processes that are required. So, if you just look at anything that we are using, right, it is not like, we started digging and suddenly that component popped out of earth, right? So what does it mean? That means all these components have been produced in some process, in some way, which is what we call as manufacturing. So the materials and manufacturing go hand in hand. You have to have material development and the materials have to be put into shape that we can make use of. So this another way of looking at the metallurgy materials field is development of variety of materials so that an end product, can be made and we can make use of in our daily life, right? So materials manufacturing kind of will go hand in hand. This is from a very broad application perspective. Materials and manufacturing really go hand in hand, right? So coming to the basics part, what would be metallurgy, material science? The science of materials development, how we process it, and what is the kind of a structure. In our parlance, we call it as microstructure. So what microstructure simply means that, normally we cannot see with our naked eye. So we try to, prepare the material, the samples, and look at it at a higher magnification. Then we begin to see introducing features inside the metals and materials. That is what we call as microstructure. And as a metallurgist and materials engineer, this microstructure is one of the main aspect of the science of metallurgy and material science, right? Because the microstructure that we don't normally see with our naked eye is what is important in determining how your product is going to perform. See, one of the comment one of the audience made is the behavior, performance, and all that, right? So the microstructure really plays a key role in determining the behavior of the material, or if you will, the product. So the science of processing and microstructure is one of the main aspects of the science of the materials engineering, right? And of course, the property measurements is also very important, because if you think of any product, you will always associate some requirements for the product. You may say, oh, I want this product to be soft, or you may say, no, ye kadak hona chahiye, this should be hard. So you quantify them by measurements. You can measure any kind of a property, be it the mechanical property or the physical property or the electrical properties or the magnetic properties. So again, property is a very important aspect in metallurgy, material science, because whatever products we make, we want to make use of in our life, there are specific property requirement. For example, you are going to make some, dental implant. That will have very specific property requirement. My colleague Parag is an expert in that. I hope maybe he'll touch upon that a little bit. So it will have a specific requirement of properties. So that is why in the science of metallurgy, material science, we talk about, the material development itself and how we are going to process to produce whatever shape we want, and try to understand, beneath our naked eye at high magnification, if you have to go really deep into the material, what is this microstructure? And finally, what would be the properties, right? So the science of metallurgy, materials is really trying to link all this thing. You can think of processing, microstructure, property in our material and products. So this gives us a real broad perspective to have a feel for what is, if you want to kind of understand what is metallurgy and what is material science. So you can have this kind of broad perspective, right? And in terms of materials itself, there are a wide range of materials. There's no way to completely talk about it in a short session like this, but you can broadly think of metals, right? You can think of ceramics, you can think of polymers, you can think of composites. These are traditional materials classification, right? Metals, of course, steel, copper alloys, aluminum alloys. So these are the common thing. And there are wide variety of materials. This is just to give you an example, few examples, right? And the end application that we need in our product many times will drive materials development, be it improving the existing materials or coming up with a newer and newer material. So this is how the entire domain of metallurgical engineering and materials engineering can evolve, and this is where the excitement is. Okay, so this is basically to touch upon one of the aspects which I wanted to deal with you, which is to have an idea of what is metallurgical engineering and materials engineering. The other point I would like to emphasize is, unlike many other fields which could be standalone, but our field of metallurgical engineering and materials science and engineering is highly interdisciplinary in nature. So just to give you a feel for it, if I take our institute IIT Bombay, is there any comment or question?
No, sir, no, nothing is there.
So if you just think of I'm just thinking about IIT Bombay. So at least 50 to 60% of the research that is being done here will have something to do with material science, metallurgy, material science. This is cutting across department, not just my department, metallurgy, materials department. We have people from physics, chemistry, mechanical, electrical, you name it. Almost all the departments are actually pursuing, some kind of a materials activity. So the point I'm trying to make is that this field is highly interdisciplinary. So you really want to make a big impact, you will see that there will be an interplay that will be needed from variety of experts. You will need physics inputs, chemistry inputs, mechanical engineering aspects, electrical. So it's that way a very exciting field, where you can actually talk to these various experts and do something which can be very impactful. So this is another point which I really wanted to emphasize in terms of the interdisciplinary nature of this field. So I think this is the broad background which I wanted to give you before now I can request my colleague, Professor Parag Bhargava, to take over. If you guys have any comments or questions before I hand over to Professor Parag Bhargava, we can take it. Otherwise, we can have Professor Bhargava to share his impression, then we can come back to the discussion at the end of the program. So thank you for this, listening to me, just giving you a broad perspective. Yeah, thank you.
So shall I share my screen? Is that fine now?
Yeah, go ahead, Parag. Yeah.
Okay, thank you, Professor Narasimhan. And thanks, Professor John and the college, for giving me this opportunity. Professor Narasimhan also sort of is responsible, for me to be able to, share some of my thoughts with you all. So I have a small presentation. A large part of the presentation are pictures. So hopefully I'll not take a lot of time, but still, maybe I'll try and see if I can finish in 15-20 minutes. So I'm going to share my screen now. Just a minute. Just a minute. Okay. Are you able to see?
It's visible, sir.
Sorry.
Visible.
Okay. Right. So I'm going to go to the presentation mode. All right. So what I've done is, some of my slides are, in the sense, in the spirit of assuming that, there are children here as well, school children. So it's in that spirit. All right. So I'm going to get started now. So anyway, as all of you can possibly, I mean, just by seeing, I think you will realize that I'm first just talking about starting from science. Okay. Of course, everybody knows it, but all I'm trying to say is when we want to do science, what is our main motivation? Learning about nature and its ways, right? It's distinct from engineering, right? And some of us are excited about science and some of us are excited about engineering, but you will see the department that me and Professor Narasimhan heads is actually allows us opportunities to pursue both science and engineering. So that's also the other fun part of it. Right. So anyway, I'm just sort of repeating here science, which mainly, is about knowledge, which covers general truths of operation of general laws. Okay. Another quote from here, Einstein, that it's science is something to do with curiosity that we have. Okay. And that is a very famous quote from Einstein where he says, I'm neither specially clever nor specially gifted. I'm only very, very curious. So to do good science, one has to be very curious, essentially, right? Now, what is engineering? I mean, I put some words, okay. It depends on how you think about it. One possibility of thinking about engineering is that, now suddenly it's, I mean, of course, you have to understand nature, but it's distinct from science that if you do engineering very well, as represented in the pictures, you can transform lives, right? You can make lives of people comfortable, secure. You can make probably people happier in some sense and also give them tools which help you to learn. For example, our laptops or mobile phones we are using, for learning also, for our self-growth, right? So safety, security, self-growth, happiness is what engineering is sort of capable of bringing. The other thing which I always say about engineering is about problem solving. And I don't mean to say just simply solving equations, but engineers can solve real problems, right? That's where the importance of engineers and engineering is. Okay. So here is again engineering technology. It's basically application of scientific and mathematical principles, but it involves some practical aspects, right? You have to apply these to practical ends. And as Professor Narasimhan also said, it involves manufacturing, design, manufacturing, operation of efficient and economical structures, machines, and all of that. And like I said some time ago, engineering is driven by problem solving. And I always believe that one of the best attitude an engineer can have is that every problem that you encounter as an engineer has a solution, provided we start looking for it. Many times, we are sort of, not really going after the solution, and that's why we may not have it. But if we have that attitude very clearly, then normally one would end up arriving at some solution to every problem that you encounter. And that's the real engineering approach. Okay. Now, since this session is about an introduction, so to say, or talk about metallurgical engineering, our department here is actually named, as I said early on, it's named Metallurgical Engineering and Materials Science. And I find it interesting because both the words science and engineering are represented in the name of our department. So we can, or we have opportunities, we have colleagues like that where we pursue both science and engineering. Okay. So remember, we call our department in short ME and MS, MEMS. Okay. I'm going to use that acronym later on. Okay. So I am going to go forward now with this. So here it is. I mean, of course, all of you know about this. As Professor Narasimhan again said, can you think of, like on top of this slide, if you can see, it says, is there anything that is not composed of materials? Can you think of something like that? And you can say that's a stupid question, right? Can there be anything which is not composed of materials? But anyway, the reason I'm bringing up this question is that one realizes by asking that question that everything that we use has to be made of some materials. If not metals, something else, right? So whatever you are seeing on the slide is made of something. And that is why this department or this specialization is so important, right? And I'm just sort of joking here, the more materialistic, but in quote marks, the more materialistic as in the more we think of materials, right? Not the money, but the more we think of materials, okay, the better we will do it as materials or material scientists or metallurgical engineers, and we'll discover more and more opportunities. Okay, so we need to be materialistic in that sense. Okay, I hope you get the joke. Anyway, so moving on, I have just said that imagine a world without materials. So a world without materials would be, I would imagine that there is nothing, right? Because as I just said in the previous slide, a world which has no materials has actually nothing in it, right? So that is why it is so exciting. Now, if you think about the applications of materials, again, lots of applications, it's endless, right? Professor Narasimhan said, when you think of clean water, which is a very important issue, even now in India, there are a lot of people don't have access to clean water. How do you get clean water? What materials you use? Arsenic problem is there, fluoride problem is there, some insolubles are there. So everywhere there is this, you need to develop materials which will give you all of this. Okay, uninterrupted electricity, whether it is clean energy, for example, nowadays, or whether it's the conventional thermal power, if you want to build turbines, anything. Wireless communication, you want to use, certain kinds of antenna which use dielectric materials. Okay, you need to, everywhere you have to think of materials. Like Professor Narasimhan already said, right? Automobiles or televisions, okay, CDs and all kinds of memory devices, so you have to always think of materials to be able to make these devices very well. And every company, at least in the developed world, which is manufacturing many of these things, will always want to hire materials people or metallurgists, right? So that makes you feel that, look, this is really a very exciting and an interesting discipline. Okay. And of course, because of all of these reasons, you would realize that whatever we do through research in material science and metallurgy That forms the backbone of all other engineering departments. See, if we don't work on semiconducting materials, if we don't work on single crystal growth, if we don't work on super alloys, if we don't grow single crystals of super alloy, and we can't make turbine blades for aircrafts, right? So everything that we are going to do, civil engineers will use the steel, right? Chemical engineers want materials which can tolerate all aggressive environments. So every aeronautical people will come and tell you that, look, give me some exciting, I know, composite materials which have superior properties. So all developments in other engineering fields are basically, in a way, also dependent on the research carried out by material scientists and metallurgists, right? And we may think of ourselves, when we come to engineering college, when we teach, or when you students come to engineering college, everything looks very compartmentalized. Okay, I belong to electrical, this person belongs to metallurgy, this guy belongs to mechanical. But the real world doesn't look like that, right? Real world always has no boundaries. When you solve engineering problems, you either work with every kind of engineer, with people from different engineering disciplines, or you have to enhance your knowledge in different disciplines. Even if you are a metallurgical engineer, you need to know electrical, you need to know a little bit of mechanical and all that, right? So no compartmentalization in the real world. All, as I said, all you need to solve problems and to be an engineer is you must be motivated and passionate. You must have that drive. Okay. Now, some examples, very common ones. Most of you know these things, right? This is a fact that I think Thomas Alva Edison tested few thousand materials, okay, materials for filaments before he came up with the final version of the light bulb, right? Imagine if he did, if he did test one material a week, and if he spent, a few thousand weeks, imagine how many years must have gone by. Maybe he took help from people, maybe that way he reduced the time, but imagine how it must have been, a test of his patience to keep testing materials and figure out that filament, right? And all of us benefited from that hard work. After that, of course, a lot of new lighting technologies have come up, and I'll talk about one or two little later. Anyway, again, the example of an aircraft, right? You know where it started, right? He started here with the Wright brothers, extremely simple, possibly just made of wood and metal wires and all those kind of things. But imagine where the technology has gone. All kinds of technologies are embedded in these aircrafts, and they use all kinds of materials. Okay, so very sophisticated product, and has involved a lot of research before we have been able to reach where we are today. Okay, another example, this is an interesting picture. If some of you have not seen, this is sort of history. This is the starting point of a PN junction. These were large objects which were made before the integrated circuits, tiny things like these started to come, right? This is, I've written the dimensions here, right? So these were very large things to begin with before, people started to look into making all this, integrated circuits. Imagine coming from there to where we have come in terms of miniaturization. Earlier, the equivalent of a laptop, maybe in, maybe just 30 years ago, was as big as very large size building. Okay, whatever we have now, all the kind of capabilities in a laptop was equal to a huge building, maybe of the order of few thousand square feet. So the world has continuously miniaturized. Of course, that's not possible without working on materials, right? So it says by 2020, 1 square centimeter would be able to hold 40 billion transistors. Imagine the scale of that device. I mean, the feature size. It's gone to just a few nanometers, right? Extremely impressive in terms of materials development. Okay. Now, again, the similar message like I listed. Okay. Material science and engineering, or material science and metallurgical engineering, for example, always is interesting and important for other disciplines. For example, ask an electrical engineer how he or she would be handicapped without those dielectric, semiconducting and insulating materials. Electrical people would be completely handicapped, right? If you don't have those kind of materials. How would a mechanical engineer do if he or she did not have these cutting or machining tools and various grades of steels and alloys? Impossible to go forward, make all these kind of machines or gears, or those heat treatments that you need, hardening, case hardening, all those kind of things, right? How a chemical engineer is delighted to use the chemical resistant materials for pumps and seals. There are many people, who are not aware of materials. They would like to always speak to metallurgical or material science people to understand what they can use for specific applications. Or an aeronautics engineer is happy to use lightweight, high strength materials. And literally, I mean, I'm not exaggerating. This is just the tip, literally tip of the iceberg, that what this department is, okay, or this specialization is. Okay, now I'm going to talk about some opportunities, and most of it is pictures, okay, so that we can wind up quickly. And in the end, we can have that general discussion which Professor Narasimhan mentioned. Okay. Now I'm giving you some examples of opportunities from our own work, okay, our own research work, and you will see, okay, what I mean by opportunities. See, this is some research work which some of my students very early on when I started my career were doing, and that technique is called gel casting of ceramics, or in this case, say gel casting of alumina. So in this case, what we do is, it's like somewhat like powder metallurgy, if some of you know. So you work with materials in form of powders. So we have ceramic powders. Okay, we take solvent, we make slurries or suspensions, and we add some monomers, things which will give you finally plastics or polymers. So you add some monomers, and these monomers must be such that they dissolve in the solvent. You mix it all up, you get a slurry. You remove air bubbles because sometimes air bubbles get trapped, and you add an initiator and catalyst. Why do you add that? You want to polymerize this monomer. So there is a monomer which is soluble in the slurry. You cast it into certain dyes or molds. Okay, before that you add an initiator catalyst. So imagine you are pouring a liquid, a suspension, into a mold, right? And you have added an initiator catalyst, so that monomer will polymerize. Now what happens is, when the monomer forms the polymer, it basically solidifies, not really that way, not like a molten, but it basically goes from a liquid to a solid. It turns into like a gel. Okay, and all the ceramic powder particles are trapped there. So you form a shape. You can then remove that shape from the mold, dry it out because it was having solvent. Okay, if you like to machine it in the dried state, you can do that. Then burn the organics, the monomer which converted into polymer, and then you sinter. Sinter means you harden the material, you form the component, right? So the particles tend to come together. Okay, I'm not going to use very technical words because of the audience which may be very broad, right, from school children, but use the word sintering means things join to each other, they get bonded, okay, and they get densified, and you mark the component. And I'm now going to show you pictures. Here are some pictures from our own research, and these are all shapes that we made by that process which I showed you, right? Gel casting. So we could make very tiny things like crucibles with 21 or 20 microliter, and going to centimeter square, kind of several hundred centimeters square kind of large plates. All of this we could produce by gel casting. And this was one work done by my early PhDs. And even during the PhD, one of the students, when he was making these, some supplier to our department saw it and said, "Oh, can I buy these things from you?" And the student was really excited, and we ended up selling it to the supplier who was giving us raw materials. Okay, so those were some exciting things. And finally, some students earlier I used to be in IIT Kharagpur, so some students who were interested in seeing all this, they said, "Why don't we use all of this to start a company?" Okay, which is what I say when I say about opportunities. So when you do all of these kind of things and people see it, they say, "Oh, this is valuable. Can you give it to me? Can you sell it to me?" And then some students came to me and they said, "Sir, let's start a small company." So these people started a small company. That company name is called Ant Ceramics. They were my students that time, and they have now been doing this for around 15 years. Initially, it was very difficult, but now they've become very established. This picture is quite old. So they make lots of different ceramic components using processes which are based on casting of ceramic slurries. This is like their brand name, Ants Lab, but they make lots of different ceramics which can be used as crucibles, all kinds of applications which we have in research or even in industry. Okay. And 2 years ago, they got an award also from the president. So if you keep working hard, you are patient enough, then maybe things like these can happen. Of course, they are not sort of satisfied with things. They are still working hard and wanting to do more and more things. Okay, so both of these were students at IIT Kharagpur with me. Okay, Sabyasachi Roy on the left, and on the right Ashwini Kumar Jain. Okay, now another thing, just quickly to connect with IIT Bombay. Okay, slightly different. So this same company, Ant Ceramics, what they have done is they have taken a technology from IIT Bombay. See, it says here, from another faculty member from bioscience, and they had developed, faculty member name is Rinti Banerjee. She developed this technology for a coating of antiviral coating. So what this company, because a lot of other things were slowing down, so what they did, they started making these masks with the antiviral coating, and this mask is now available in the market with the brand name of Ants Duraprot, Duraprot. Okay, durable protection, I think. So they are making, if there is a need, they make also gloves, handkerchiefs and all that, but this mask is an antiviral mask, which they have done. So my message here is mainly that once you are having this technical background, like you studied material science or metallurgy, and you start doing something like these students, ran a small company. So they became so confident of quickly absorbing the technology. So they received the technology and quickly launched the product, So your technical background comes in comes in handy. It's very useful because then you get used to this whole idea. But it's very important to do hands-on work, okay? Otherwise, you can't do such things, right? Now, another very interesting example from materials. I will not have all examples from metals. I have maybe some few things. These are all diverse. So I hope all of you have seen this, right? All of us have eaten this sometime, at least in childhood and sometimes even in our adulthood. And this is made using this kind of a machine, okay, which is very cheap, some 12,000-13,000 rupees. And in this machine, basically there's like a spinneret where there are fine holes, and you have a heater here. So you pour that sugar syrup in here, and you heat, and when you spin it, basically this inside thing spins, and that's how you collect the fibers. So one professor of Indian origin recently gave this idea. I had attended his talk at Stanford. He is a graduate of IIT Kanpur. He said, I can simply use the same cheap machine. Instead of sugar solution, I'm going to add polymers. And polymers, have very low melting points. So he started spinning polymer fibers using this machine. And the interesting thing he said is, by using these polymer fibers, by spinning polymer fibers out of this machine, you can make face mask for this situation which we are facing for COVID. Because the N95 masks, which are made by 3M, are all polymer fibers. So you can spin polymer fibers, you can compact them, make sheets, and then eventually make masks. Okay, this was very exciting. Now, the other reason why I showed this was, we developed a similar machine in our lab. We didn't buy, and we made ceramic fibers, high temperature fibers. Okay, I'm going to show you pictures. So the ceramic fibers that we make are able to take, their melting points are of the order of 2000 degrees. So what is the use? We use these ceramic fibers to make high temperature thermal insulation, okay, for making furnaces. So if you see, these fibers that you see are made by one of my students in the lab, okay, and the diameters of these fiber is smaller than our hair, okay, because these are like between 10 to 50 microns. So they are typically smaller than our hair, and you can clearly see the crystals, or for school students, I'm saying these things are crystals, but for metallurgists, you can say that these are all grains, and you can see the grain boundary. And these white things, the gray thing is alumina, the white things are all zirconia. Why did we add zirconia and alumina? Zirconia helps to restrict the grain growth, because when these fibers are going to be used at high temperatures, the grain growth will occur and the strength will go down, right? So we added some other material to limit the crystal size so that the properties of these fibers are retained. These fibers remain strong even at high temperatures. Okay. So these have very interesting applications, like, you can see they have high temperature resistance. You can make boards out of these fibers by compacting them, and then you can start making very lightweight furnaces. So if you use this kind of material, the furnace can get heated and cooled very fast because it doesn't soak too much. It doesn't take up too much heat itself. The thermal mass is quite low, right? So very good opportunity. Nobody is making high temperature alumina fibers in India. Okay. This is the picture, these ceramic fibers look like this when we spin it out. Okay. Now, this is just I thought it's interesting to see that I was teaching a course here in IIT Bombay for our BTech students. These are first year students. And I told them that can you please make two things, okay, out of these milk bags. All these pictures that you're seeing are milk bags. So they have washed them, they have cut them, and then they have welded using this kind of a hot heat gun. And finally, they have made two nice things. You can see some picture here. So they have made some pots. Maybe these pots, if you make it a little larger, it can be used for making planting things in it. So that way it's a good use of milk bags. And they also made really a very good raincoat. This is our one undergraduate student, and they tested the raincoat. They showed me in the class presentation. They tested it under the hostel shower. They went to the bathroom and just went under the shower and said that, look, the raincoat is very nice. You can wear it perfectly and all that. And they gave me a cost calculation also, that how cheaper it will be as compared to buying from outside. So both purposes, right? Some recycling and you can get a useful object. Okay, both the things. So things like these, sometimes we try with our, undergraduate students also, and that makes them very excited. Now I'm shifting to something which Professor Narasimhan referred, materials in our lab, and this is a very exciting development. Nowadays the best material, I don't know if you have heard, but the best material, and it has a Kerala connection also, I think, in some sense. Okay, so the best material for dental applications is zirconia. Okay, it is a doped material, doped zirconia, yttria doped zirconia, but let's think of it as ZrO2. What is the Kerala connection to it? Kerala beach sands are rich in zircon, ZrSiO4, zirconium silicate. And zirconium silicate is the starting material to make zirconia. Okay, but it requires a lot of complicated processing. Okay, it's not easy. From zirconium silicate, there are many companies which will make zirconium chemicals like salts, like zirconium oxychloride, and then you have to do many steps. But I'll quickly explain this. See, these are pictures when you go to a dentist, and if there is some issue in your teeth, something is broken or whatever. So first thing the dentist will ask is to bite into a soft material. It will look like this. So this is like your bite. If I bite into the soft material, once you get this bite, okay, it sets, and then they cast a plaster of Paris, like dental plaster, into it. So you get the positive of it. Okay. Now you take this, and the dentist will send this to a dental lab, and the dental lab will make this. And then the dental lab guys will have a 3D scanner. So they will scan this into a 3D scanner. So they will get a CAD file. Okay. Another shortcut is, nowadays you don't have to do this, but there are some 3D scanners which are called intraoral. So they can enter your mouth, right? You can directly, the doctor will only put it, and without doing all of this. So it is little pleasant. This is unpleasant. So this is pleasant experience. Directly you'll get an image, and that image the dentist will send to the dental lab. Now, once you have this picture, the dental lab guys will, digitally rebuild your broken tooth, okay, in their software. And you know that which part you have built. So that part which you have built digitally, that part is now broken down into STL files, okay, or it's converted into STL files, and these STL files are now transferred to a CNC kind of a milling machine. This is a close-up of a CNC milling machine, and the input is, this is the zirconia disc, which is made from powders, from zirconia powders. Like I said, you make zirconia nano powders, you press them by isostatic pressing, you pre-sinter them, so you keep them porous, so they are machinable. You put them here, and this milling machine, based on this 3D scan, will mill it and will give you something like this. So these are lots of different crowns or caps for different patients. Then they break this apart, okay, then they machine it a little bit on the sides, the parts which got broken, and after machining they will put some kind of a, glass kind of a material coating, and then it starts to look like a natural tooth. Once they make this, they will send to a dentist, and the dentist will use a cement and put it in your oral cavity, and then it may last for 20 years. And you can't believe that this material has a strength, ceramic material has a strength exceeding 1 gigapascal. Okay, so they will last a lot, and they just look like natural tooth. Nobody can tell that it's an artificial tooth. What is our connection in material science and metallurgy? We wanted to make this powder in India. Nobody makes the powder of this material commercially in India, so that then we can try to make these discs. Okay, so this is where I'm repeating a little bit. So for making these crowns, you need these discs, right? And these are all the advantages I told you of zirconia. And as I said, zirconia discs require very high quality zirconia nano powder. By the way, if you want me to stop sometime, please tell me, okay, if I'm taking too much time.
No problem, sir.
So you take these zirconia, you need the zirconia nano powder to make these zirconia discs. And once you get these discs, I have shown you in the previous slide, you can make all these dental crowns. And like I said earlier, no manufacturer of this zirconia powder in India, even though like your Kerala beach sand and Orissa beach sand is rich in zircon, we have the raw material, but unfortunately we lose the precious resource. We export it as, cheap sand, but we buy it as a very expensive processed raw material. And one of the leading companies is called Toso in Japan. Okay, so we were trying to say that let's make like Toso type of material in India. Okay, that was our target, and I had one PhD and several master students work on it, and I'll show you some pictures quickly of it. So these are the characteristics of the powder. The powder must be easily dispersible in water. Okay, this nano powder. so that I can spray dry it into granules. Only when I get granules, then the granules can be used, like these are aggregates, controlled aggregates, then those are used for in isostatic pressing. I press them into discs, and then you saw those disc pictures, then I'm using it in other applications, right? One very important thing is my powder must have this kind of a characteristic, that it should not be anisotropic, such that finally when the crown is made, the crown, when it is sintered, should not have anisotropy. Otherwise, it will not fit in the patient's mouth, right? So because the crown, when it is made by milling, is little larger, and if it will shrink isotropically, then it will shrink and fit the patient perfectly. Okay, and these are some other details. I don't want to go into it. This is the process we use. The process is simple. This zirconium oxychloride, like I said, comes from beach sand. Okay, it is made from that. So we use this chemical, we use yttria, we dissolve it in nitric acid. We have a solution. We add it in ammonium hydroxide. This is called co-precipitation, maybe like simple chemistry. And we get the precipitate. The precipitate is basically zirconium hydroxide with yttrium hydroxide in it. Then we dry it. We wash it first. Why do we wash? We want to get rid of chloride, nitrates, everything. Then we dry it. And after drying, when we calcine it, the hydroxide decomposes and gives us the nano powder of the oxide nano powder. Okay. So these are the pictures. I have not shown you powders or pictures, but let me tell you, we are now able to make powder as good as Toso almost. Okay. And you can see this is the picture of our sintered materials from our powder, and you can see this bar, this white line is 1 micrometer. So our grain sizes are smaller than 1 micron. Then you can imagine hardness and strength goes up, and we almost achieve the same kind of microstructure as we get with commercial powders. This is what is obtained from Toso kind of powders. Okay. So it's a beautiful material. Now we are, trying to see if we can scale it up. We got a project sanctioned, but somehow there was some issue. We didn't get the government money. I want to now try it again to try to scale up this process. Okay. And one more thing I wanted to share, because of our interest in this dental materials, one of my old students, from IIT Kharagpur days, he had some friend and they invested, and we started a dental lab, okay, which is running in Indore, and they have all the sophisticated machinery. And we have that dream that maybe we should be able to make our own materials, test it out at this commercial dental lab, and someday, also commercialize it for, benefit of our country, so that we get, better, good quality, low cost materials within India. Okay. Now, another very interesting opportunity. It's a big opportunity. All of you are aware of solar cells. When you look at solar cells very closely, you will see all these lines running on the top of the solar cells, right? Each of the cell. What are these lines? These lines are basically made from silver, okay, from a silver paste, special kind of silver paste, and you heat treat them. But basically this silver makes contact with the wafer, and this is how you collect your charge carriers or the power out. This is how you collect the power. If this silver contact was not made, you would not get the power. So it's a very important product, and if the quality of the paste is right, contact is made correctly, then you would get the right kind of efficiency. Only thing is, this is a very challenging opportunity. No Indian manufacturer. These are the details of these lines that we have to screen print. This is an area dominated by very large companies. All of them are like billion-dollar kind of companies. So it's very hard to compete with them. But we were thinking, since nobody is making in India, we said, let's try it. Okay. So there is some metallurgical connection. Hopefully you can see, right? And we have this center called NCPRE in IIT Bombay, which also helps us, we collaborate with them and then try to, make these solar cells and do the testing. Now, what we do in our lab is, this is the interesting part from materials or metallurgy viewpoint. If you see that white bar is 1 micrometer. So we make all these silver powders in our lab. Okay, you can see the zoomed in picture. These pastes, this is the picture of another picture of paste. So these pastes have silver powder. These pastes have a special glass powder. Then we add some organics, and then we do high shear mixing by what is called a 3-roll mill. So we put all these materials together. The glass powder, as I said, we make it ourselves. We melt the glass, we cast it the glass, and we make powder out of it. We make these silver powders. Okay. And after mixing, after high shear mixing, we make this paste. And this paste has to have very special flow behavior. And then we take this paste and we use something called a screen printer. And this is what is printed here in IIT Bombay on wafers to make the solar cells. And then we do characterization. I'll skip it. Now, the other thing, so this is a project ongoing and we are still working on it, and we are hopeful that we will make some good pastes, right? Because there is some science which we are still trying to understand, and we are progressing gradually in it. But with this knowledge of our ability to make silver paste, we are trying to make some other products also. If you look at this now, this bar is 1 micron, and the powder particles are much smaller than this, right? So these are our silver nano powders that we are able to make. These are very interesting. There are many applications, like in antibacterial applications. Even if you make these masks for COVID, you can put this silver nano powder in it. Okay. But we use it for other applications also, engineering applications. And then we also made silver nanowires. This small tiny white bar that you are seeing is 100 nanometer. So you can see the diameter of this wire is like 100 nanometer, which is like if you take our hair and if you split it maybe in 1,000 times or even more than 1,000 times, then you will get this size. So these are so small wires that we make of silver. And it has very interesting applications. If you coat these silver nanowires, for example, on glasses, okay, it will keep the glass transparent, but the glass will become conducting. And then there are many applications for making devices. Another thing that we make in our lab is these pastes, another kind of paste, which are room temperature paste, and we can print it on polymers. Like this kind of pattern is there in every computer keyboard. If you open up some used keyboard, you will see that there are these membranes, 2 polymer membranes, PET, on which you have silver patterns. So when you press a key, basically you are connecting these silver patterns so that your action happens in a computer. Or in many other devices, you have these silver printed into circuits and patterns. So we make these pastes. This is a commercial paste which is printed in our lab, and this is our own paste. So we are able to print it nicely. One last thing which we are doing with silver is we are trying to make a pen in which we'll fill a silver ink. We have already made it. But when we write with this pen on paper, the line will be conducting. So you can make conducting lines on paper. You can make circuit on paper. Okay. So we have made this pen. We are still trying to improve it. It works for a while, but then it gets clogged. So we are still working on it. And we'll try to launch it. Okay. Many of these things, some of my own undergraduate students, metallurgy students from IIT Bombay are working on this to try to launch these things as a product. So I see them all as opportunities in metallurgy. Okay. Now I'm giving you some different thoughts suddenly. Okay, I'm switching my discussion. See, I am sharing here with you basically some data on Samsung Electronics. Okay, in 2019, this company Samsung Electronics, see, remember Samsung was not in electronics maybe 20-25 years ago. They were only in shipbuilding and some construction and all that. But they grew so fast that in 2019 their revenue of electronics division, not the other divisions, was $206 billion. You may not be able to calculate. $1 billion is 7,000 crores, okay, rupees. So it's too much money. Okay. Now, interestingly, Samsung Electronics R&D spending in 2019 was $16.6 billion, a fraction, right? Maybe like 8%. But if you convert to Indian rupees, it was 1,24,000 crore rupees. One company, Samsung, spent on research 1,24,000 crore rupees. What I'm trying to say is, when are you able to spend so much money on research? When you are able to do good business. When are you able to do good business? When you are able to do innovations. So it's very important to innovate, build big businesses within our country so that we can spend on R&D, and then only we'll be able to build more and more products. Now, another interesting thing, I mean, they have 63,000 researchers all around the world, 42 research facilities. Now, one very interesting thing I found is, I found 2019 budget of entire education in India, okay, not just higher education, complete. That budget was 94,854 crores. The budget of one company from Korea, R&D budget, is greater than our entire country's education budget. Can you imagine? So what I'm trying to say is, we should try to build such companies in India that then we imagine, if we have that kind of companies in India, what will happen to our education budget? And then all of us will have much better facilities for research, for everything, for learning and all that, right? So very, very important to build products, very important to build these companies. And I feel that's a big opportunity in metallurgy. Now, quickly, a few more slides, I think maybe 7 slides, just pictures, and then I'll end. This is a very interesting thing which all metallurgists should know now, something called additive manufacturing, like 3D printing. But there is a new technique, relatively new technique, called a direct energy deposition. So earlier people were doing with powder bed, but there are many advantages by doing this direct energy deposition, in which if you start with powders, these machines have like powder feeders. Okay, so these powder feeders are coaxial along with laser. So you have this whole assembly, and this whole assembly looks like this in real. Okay, and here, even if you are not able to see, these metal powders being fed continuously along with the laser. So it falls over there. The laser melts the powder and starts to build the layer, right? So you keep building layer, and that is how you can build three-dimensional shapes of complex shapes just by using this technique. And this technique is why it has become more interesting now, is it's a very fast technique compared to those powder bed kind of techniques. Second thing is, in this machines, DED machines, you can have multiple powder feeders. So you can make composites, you can make alloys, you can make graded materials. Beautiful machine, okay? You can do many things. And in the same machine or another, I mean, either same machine or other option is you can also feed wire and build the three-dimensional shapes. And one last thing which is also very attractive is this machine can be used to repair components. Imagine you have a very expensive aerospace component and you say, oh, look, how can I throw it? So what you will do is you will take that component, you will do a scan of it, you will get a CAD file, and then you will see where there is a, where you need a repair. So you rebuild first digitally, and then you give the tool path to this machine, and unattended, basically like robotic, this machine will go and repair the component. Okay. So it's already in use. Okay. So I'm showing some pictures. See here, there's a seat using these machines. Okay. These kind of complex shapes, they're built by direct energy deposition. This component, which has multiple metallic materials, has been made by direct energy deposition. This shape, which cannot be made easily by other techniques like a rocket fuel tank, has been made by direct energy deposition. These pictures are from this company Instech. Beautiful technology, lot of metallurgy here to understand. People are studying its corrosion, all kinds of things. Okay. And slowly India is also getting into it. We are also hoping that IIT Bombay will get these machines. I'm sure we'll get in the next 1 year, we'll have multiple these DED machines in our campus. Okay. Another one, ceramic 3D printing. Okay. Look at these parts. These are basically ceramic dental implants. Without any mold, you are able to make these components 30 seconds per implant. Beautiful machines. Okay. And this investment casting core, ceramic core, has been built by ceramic 3D printing kind of a technique. So all these are now becoming not just prototyping, but manufacturing techniques. Okay. I'm going to skip this. All I wanted to show here was that if all of us, get determined, I think we can also start to do many of these things, as long as we, understand where the problems are, and if we keep our engineering attitude of solving these problems. I just put a small picture of a product here, Scotch Brite. All of you know this. This product, which is from a 3M company, is basically like a polymer ceramic composite, polymer fiber and some ceramic particles. And in India itself, this company sells maybe a few 100 crores worth of this product. Why can't we make it? Anyway, I just wanted to say that. Pictures of wind turbines. Okay, you need to make composites here. Pictures of metallic foams, beautiful materials, right? Metal foams. You can foam metals by various techniques, and it will give you many, many interesting applications, including, some kind of heat exchangers and crash resistant structures. These are some ceramic membranes which are used to purify juices, all kinds of liquids. Okay. So these are all the membranes, and if you zoom it in, it looks like this. You have a nanoparticulate layer and then larger particles. So this layer helps you to filter things. This is picture of LEDs, all, multi-layer materials. Okay. All kinds of materials involved, but as I said earlier, material processing only will give you LEDs. I think India still doesn't make LEDs, but imagine all the lighting industry is now shifting to LED. And completely different, rice husk. All of you eat rice, right? This rice husk is rich in silica, and there are a lot of people who have done this research that you can take rice husk, when you heat it, you will get very good quality silica. Of course, there are impurities, but you have to purify it. And you can also make silicon carbide, extremely hard material, out of this. Another nuisance material, fly ash, which thermal power plants generate, can be used to make many, many things. Okay, many ceramic applications. And this is a list of many ceramics that you can make. And there is a big kind of commercial angle to this fly ash kind of materials. These are beautiful materials called ceramic honeycombs, which are used in catalytic converter in every car nowadays. And through these honeycomb, the engine exhaust passes, and there is a catalyst coated inside, which will convert harmful gases to, gases which are acceptable and don't create problem to the environment. Very difficult to make, but very interesting technology. And there are people who have used these honeycombs, ceramic honeycombs, for other applications also. Like if you weave a wire through it, and if you pass current, it gets heated, and then if you blow air through it, you can make heated air blowers. Beautiful applications. Okay. And there are many other applications also, which I want to skip. Now, this very interesting application, all of you have seen ball bearings. Most of the ball bearings are made with metals, right? Steel and all that. right? But the best ball bearings today, which are very expensive, you cannot, you can't compete in cost with metals. But if you buy ceramic ball bearings, they are so amazing, because they don't wear out. So they are used in very high grade vacuum pumps, turbomolecular pumps, which go at very high RPMs. Okay, they are used in windmills, because windmill you don't want to dismantle, so they are maintenance free, and in helicopters and many other applications where you want maintenance free kind of ball bearings, which are wear resistant. Beautiful application, right? In India, I think we are not making these, but again, countries like China, Japan, Germany, and all that, and Korea are making all of these. This is just like a material to make lasers. Okay, this is a neodymium doped, yttrium aluminum garnet. Okay, this material is used to make lasers. Imagine, and these ceramics, when made into fully dense materials, are transparent, and they are laser hosts, and these lasers are capable of burning holes through metals, which all of you are aware. This is another application, and I'm almost about to end. This is a sodium vapor lamp. Some of you would have seen, but the only reason why sodium vapor lamp works is inside of this part is like a ceramic tube made out of aluminum oxide, so that you can put the sodium vapor inside it and it doesn't react, and it gives you all the lighting. Very interesting application. What is this picture? This picture is basically a zoomed view of a ballpoint pen. This roller is the ballpoint pen. Why am I showing this? This is a beautiful application. This is made of metallic and ceramic, tungsten carbide and cobalt. These balls are made out of tungsten carbide, cobalt, very hard material. So imagine, it's very close to diamond in hardness. But when you have such a hard material, how to make it into a sphere is the challenge. And these rollers are still not made in India. So imagine, big market if somebody can actually start making in India, possibly, I'm thinking. Okay. This is, I've already told you, and I think I'll skip it, I think. And this is the final slide. I just wanted to say for all of you, for the students, particularly young students, I'm just calling it a toolbox. All I'm saying is, to become an engineer, to be a problem solver, these are the qualities you need. You need to take a lot of initiative. You should not wait for others to come and tell you many things. So take a lot of initiative, think about things, try to observe things around you, try to observe problems, and think of, solutions. And then slowly, as you get used to it, you will start to develop that engineering attitude. You should always practice thinking. And one of the ways I can suggest to you is, many times we are used to in our schools and colleges to answer questions. But if you are really interested in developing your thinking, one possibility could be, take something in your mind or do it with your friends. Imagine if I were to tell you, scotch tape, or I tell you like a pencil, and I tell you, okay, take half an hour and think as many questions as possible. Write down as many questions as possible. If you are a group of friends, don't share your questions with each other first. Keep writing questions and see where you will stop, where you will end. Don't otherwise give up till you can keep thinking questions, and later on share those questions. And I'm telling you, you'll find it so exciting when you see all your questions. If you are a group of friends and you do it, I do it in class sometimes. Okay, and when you answer those questions, I can tell you that you will be the expert on that topic immediately. And again, one more suggestion: don't go to Google to look for answers first. First, think of answers after you ask the questions. First, try to think of answers yourself. When you can't get after working hard, then you go to Google, because Google kills your thinking, right? Inquiry, that is related, I already said. You should always build your imagination, and there are many ways by which you can build imagination, but all of these things you really need to become a good engineer. Of course, you should focus. You should not take interest in everything that comes in front of you. Otherwise, you will never become an expert in something. I mean, as you grow up, slowly you have to focus. One very important thing which I always tell many people is, try to keep an idea book. As you observe around yourself, at your home, if you see some problems with a door, with the wall, in the kitchen, try to note those things down. Okay, and if you see some problems, and as you think of solutions, try to think of those solutions and note them down in your idea book. No idea, remember, no idea is stupid. Every idea may start as a stupid looking idea, but as you become used to noting ideas, one day you will get some bright ideas which you will be able to do something with. And it is not even necessary that you have to have an engineering degree to actually be like an engineer. So think about this, have an idea book. And of course, lastly, do not miss out on learning from everything and everywhere. No matter where you are, no matter what you do, if you have a positive attitude, you can learn from everything and everywhere. I think I'll stop here, and then the organizers, Dr. John and Professor Narasimhan, and I'm around. We can we can discuss it. Okay. Thank you for the opportunity.
Thank you, sir. Narasimhan sir, do you want to add up anything?
No, I just want to only add, I think Parag has covered very nicely the career opportunities also. That was the last topic I kept in mind. But I only just want to add a few comments on the career opportunity. See, right from the time I was like a JEE student till even today, the overall pattern of quote unquote student preference almost remains unchanged. Like the hierarchy in terms of preference would be like electrical, computer science, and maybe then mechanical, then probably civil metallurgy is like somewhere at the bottom, right? So this is a kind of perception. People seem to think that there are opportunities and finally wealth making opportunities, getting good jobs remain only in that field. It is not to say that those fields do not offer us opportunity. Obviously they offer opportunity, but what I want to comment here is, for the last several years, if you see, there is a huge job market for what I would call as a non-core sector. So if you are targeting that kind of a job, then it hardly matters whether you're graduating materials engineering, metallurgical engineering, or mechanical or computer science, right? There are many IT jobs, analytics job, finance jobs. I'm just talking about so many non-core jobs, that anyway you'll have access, even with materials or metallurgy, just like a mechanical engineering guy would have. But in addition, you're going to have so many additional opportunities that is very unique to our discipline, right? Like what Parag was emphasizing, right? So if you really get excited about the core, the kind of stuff you can do with the kind of engineering mind that Parag emphasized, that nobody else can do. An electrical engineer, or let's say a computer science graduate, there is simply no way that person can do the kind of material innovation you can do. So that is what is very exciting. So you can always get into this discipline, and if you feel okay, I've had enough of it, all the other opportunities that let's say a computer science guy would have anyway will be available to you, right? You can go to the your IT sector or analytics sector very easily, but vice versa is not possible, right? A computer science guy suddenly cannot wake up and say, oh, I want to do materials today. It's not going to happen, right? It's not possible. So that is why gaining this expertise or getting into this field actually gives you an edge. So you can actually do both. You can go to the non-core sector if you think that you want to pursue your career, and that's also available to you. But in addition, this excitement of materials field is also available to you. So that is the only point I wanted to make. This Parag has nicely covered the opportunities. I think he also hinted upon the opportunity of why look for a job, why not give job.
Sure.
Entrepreneurial opportunities are also plenty. It's up to you to define your world. So all that thing really exists in this field. So that's the only comment I just wanted to add to what Parag said. To add anything to what he says is difficult, because it's like he's omni, right? He's there everywhere, and he's covered almost everything. So I just wanted to add this comment. Yeah.
Can we go for the question and answer session?
Yes,
sure. I see some questions coming up, but would you read them out, or how do you want to do?
We have multiple questions, so general questions are there.
If you want me to go through chat, that I can do, but if you want to read out, that's also fine.
No problem, sir. Whatever you prefer, no problem. Can we speak? Some people are asking for.
Go ahead.
I think it'll be nice to ask live questions. Then later on, maybe some people are shy, they only want to chat, then we can take it up later. If somebody wants to
if participants
discussion,
so if participants are willing to turn on the audio,
you
can ask the questions.
Sir, can we do a project on gel form of aluminium, sir?
Gel form?
Gel form of aluminium.
No. Meaning your question is, you want to do a project?
Can we do?
Absolutely.
about me, sir.
See, gel casting, the technique is called gel casting, and gel casting generally we use it for ceramics. There is a reason why we use it for ceramics. Okay, because in metals case, because metals are deformable, right? They have ductility. So I don't really need to, I can make shapes of metals by many other means. But you can do for metals also if you like. Okay, there is no problem with it. Gel casting is basically a shape forming technique. When you want to start from powders and make a shape, you can use gel casting.
Sir, we have a question.
In PPT, you showed some of the slides. No, sir. There, we can do 3 structures with some.
Do what? Sorry.
With some vision, you.
Janvi,
Yeah.
your audio is not.
It's not very clear. Yeah.
Can you repeat the question?
With some instrument, you showed that we can create a 3D structure on the metals. No, sir.
Oh, DED. You mean direct energy deposition?
Yes, sir.
Yeah. Yeah. What is the question?
I think.
See, somebody asked. I know somebody
asked.
asked.
Nanotubes in that, sir?
Sorry.
Is there any role? Is there any role of nanotubes in that, sir?
No, I can't hear actually. Can you repeat if anybody can hear? The voice is.
Janvi, you can type in the comment.
Maybe meanwhile we can take some other questions.
Other question.
Sir. So there is a question from Hansha. I have a doubt, sir. If the material hot tensile property is higher than tensile property, especially for composite materials, hot tensile property as well as the normal tensile property, which is more.
No, I didn't understand. What is the first word? For first word, I didn't understand.
Hot tensile property.
High temperature, right? Right. So I mean, see, high temperature strength depends on, again, so many things. I would say, for example, whatever temperature one is looking at, I would call it like homologous temperature. I'll define it at that way. Imagine, homologous temperature, basically that temperature of your interest upon the melting point. So I want to see that fraction, right? So if whoever is asking question, if you are aware, for example, if you start to have creep deformation at high temperatures, right? So it depends on what temperature. Normally, if you want to have high temperature strength for in general, of course, because ceramics have higher temperature, higher melting points. So given a temperature, let's say if you say I want a material with high temperature strength at 1200 degrees C. So you would not want to use metals, right? Typically for 1200. I mean, of course, there are some materials which will work up to 1200, maybe super alloys would work, right? But if you have still sustained load at high temperatures, and if the application permits, I would rather think of ceramic materials, ceramic composites, okay? Because these materials are not going to deform at that temperature, right? Considering the homologous temperature as a fraction of the melting point. But I don't know if that is the exact question. And I suppose the person is asking, can the same material have high strength at room temperature, as I understood? See, in ceramics, if I assume ceramics, the one criteria which will give me high strength at room temperatures is primarily density. Ceramic density has to be exceptionally high. If you make them close to fully dense, if you retain fine grain size, okay, then you can get high strength. Like I gave you an example of zirconia. Zirconia, I mean, it's rare to see ceramics, but zirconia can go up to easily 1.5 gigapascal or so, which is an exceptionally high strength at room temperature. And then these ceramic materials can have a reasonable strength at high temperatures. Okay. So I don't know if, I hope it answers the question, but otherwise, somebody can email me also. Feel free to email later on.
So we have some general questions like, so what is the opportunity for postgraduate students for metallurgy?
Oh, there are plenty of opportunities. I mean, Professor Narasimhan can also answer it, but we have enough of core metallurgical companies. There are many. I can't answer how many jobs there are, but for example, whether it is steel industry, whether it is powder metallurgy industry, whether it is coatings industry. So there is a large number of, such segments, metal forming, which Professor Narasimhan represents, automotives. So there is a long list of, companies which will hire metallurgists. They may not hire, each company may not hire them in large numbers, because I think they somehow hire more of mechanical and fewer of metallurgists, because fewer metallurgists are able to handle most of the problems. But there are all these segments, right? Everything to do with metals, alloys, but people, I think, can look for some unconventional opportunities also, like I said, Professor Narasimhan already said that metallurgy and material science offers some of the most interesting and very large number of entrepreneurial opportunities. Or you can try to work for some small companies where you will learn much more generally than bigger companies, right? Or the other thing is completely different. You can apply for DRDO kind of jobs. We have a lot of national labs, DRDO labs, CSIR labs. So huge number of research jobs. So all these are there. But, I mean, I don't know again whether it answers the question. And
So we have a technical question to how to find the microstructure at high temperature, as we do STEM
How
and
to?
OM. How to look at the microstructures at a high temperature.
Oh, yeah. See, at high temperatures, our department recently, one of our colleagues is trying to buy a high temperature microscope. So there are high temperature microscopes available now, special microscopes. Okay. So I'm saying basically it's a matter of engineering. I mean, engineers have solved this problem already, that there are these microscopes available where you can heat the material and look at the microstructure simultaneously. So this problem partly is solved as far as I know. I think our department may get it if everything goes right.
Yes, sir. If you have any questions, sir, you can ask the question, sir. Vijay Raghavan.
This is regarding the shape memory alloys.
Okay.
Already the two applications is largely in use. One is the stent in the medical field, and also in HAL we have developed this shape memory alloys for this Tejas aircraft. Just I would like to know that anything from your side you would like to say about this shape memory alloys.
Yeah, you have a generic comment, I think, but shape memory alloys in India are developed. For example, BARC has developed a lot of shape memory alloys. And in general, like for example, if I convert this question into opportunity, BRC is very, very open. For example, if some students, young people get interested to manufacture shape memory alloys, let's say HAL wants to buy them, then BARC often does these technology transfers.
That's already done. Actually, from the academic to industrial, this one we have done some parts for the Tejas aircraft. That's what I'm telling. There are two aspects. One is at academic level, another is translating to industrial and then commercial.
Right. So I think, as you rightly said, HAL has done it, BRC has done it also, I know. And maybe there can be, like, I know another completely different application. These dental, when dental, what is it called? Dentures or those things, which you put to align your teeth, that is also using nitinol wires. So there are civilian applications also of these things. So there is a good opportunity. And as you said already, that India has, established good facilities in this area.
Okay, that is what for the coming budding engineers, this would be the another area.
Sure. No, it's a nice area. Yes, nice.
Okay, nice. Thank you.
Good evening, sir. Good evening, sir. Myself, Yerlappan from Kanchipuram, sir, Tamil Nadu. So I am the faculty. So we are so blessed to hear the legends lectures, sir.
Hello.
First of all. So can you hear my voice, sir?
You can turn on the camera, sir.
Because here background is not good, sir. That's why.
Okay, no problem. No problem, sir.
Because I am without shirt because of the high humidity.
That's okay. Yeah.
Sorry,
go ahead.
Don't mistake me. So we are really fortunate, sir. So my doubt regarding to promote additive manufacturing concepts in terms of DED for low melting materials, can it possible to innovate some prototype models in engineering level, UG level, to make sure of because only additive manufacturing is mainly nowadays concentrated in our what's called 3D printing or polymer based material only. So why can't we promote to give an initiative to our UG level students in low melting materials? Is it possible to develop that type of process in engineering level, that means UG level? Probabilities are there or not? If you find anything that is, can you help us to establish that experimental setup? That's why.
Yeah, absolutely possible. There is no doubt. Firstly, I'll tell you was general answer. we as engineers have to believe everything is possible, right?
Yes, sir. Yes, sir.
Right. So we don't say that not possible. It is possible. I'm already telling you. And
Yes, sir.
within India, it is possible.
Yes,
There
sir.
are people. I can always connect you if you email me. But I know that there is a person in this lab, in an Indian lab, DAE lab, RR-CAT. Have you heard RR-CAT
Yes,
Indore?
sir. Yes, sir. Yes, sir.
RR-CAT Indore. There is one person. He has developed his own DED machine. And there are some people who make lasers or whatever. So if you really want to go actual, just like a DED like machine, it is possible to make it, right? Because see, you have to have a some kind of a powder feeder, or initially, if you don't want to do powder, best is you can just buy wire. You can start doing it with wire. If you know, certain materials are there as wires, you have to have a laser, and you have to, you know, take some risk. So always engineering is like that. Take some risk, make something, and later on you will see some problems are there. You will improve it. But surely it is possible, and this will excite your students like anything if you make it. You know.
Yes, sir. Yes, sir. Yes, sir.
So very much possible. You can email me if you need any connections or details. Okay.
So please inform to the organizer to provide an email
sure,
to
sir.
us. Sir.
My email is on IIT Bombay website. If you
okay, sir. Okay, thank you, sir. Thank you very much. Sir. Thank
okay,
you,
sir. We have one more last question, sir. There is a participant who would like to talk. Yeah, you can ask the question.
Yeah. Hi, sir. My name is Deposition. I would like to give a short briefing about my introduction. Like, then I can ask a good question. Currently, I've done my BTech in metallurgical from NIT Srinagar.
Okay.
Was like really passionate about creating new materials and all, because I think metallurgy and material science is all about, it's just like a good cook. Just put the right ingredients and you will, you know, get a great product. So just because it was NIT Srinagar will not say much, but I didn't get a good platform to create and all of that. After seeing all your work, I'm really humbled. I'm really passionate. Like, currently I'm also working in Byju's as a content writer, but besides that, I really wanted, you know, something to do with my own field, in which I've already spent 4 years working hard, but due to some reason I didn't get a platform. Also, I know I've like searched through Google in your websites and in IITs. There's a kind of a requirement that the CGPA should be 8 or more, but less than 8 will not do for a direct PhD.
Yeah, maybe Professor Narasimhan, would you like to answer this part, the CGPA 8, because our head is here. Our head can say that.
My CGPA is less than 8, but I don't think I'm less capable or I can't well.
Sure. In fact,
you can always come through GATE. You know, if you're GATE qualified, then you can always apply. So either you know, you should be GATE qualified, or if you're coming from CFTI, like you know, you are a CFTI institute, then the government has fixed. So you also have to understand, this is not the making of IIT; it's making of government. Government has given this recommendation that from CFTI we can consider candidates for direct PhD without GATE. Okay, provided their you know, grade point is above some whatever cutoff. So that is not our making. So, but then, you know, you can always, you know, if you get qualified, then that requirement is not there. You know, so if you qualify and get that, you apply. And GATE qualification is not that difficult at all, no? For you know, if you know, you've done a good program, and if you just prepare, you'll be able to easily qualify GATE.
Okay, but right now I'm working, so you know, I don't get time to, you know, balance both the parts. So
if I can say, see, the other thing is, Professor Narasimhan already gave you, I mean, the answer to what specific question you had. But remember, if you are in the right spirit, there are plenty of opportunities, okay, to be able to, if you don't get to doing, you know, higher education, even then there are lots of interesting things. It's just that, you know, you have to not lose patience and interest, okay. There are lots of small companies which are starting, which need materials people. All kinds of opportunities are now arising in India. It will take some patience, you know, and your sustained interest, I can tell you. And if you have really, if you have determined, you know, if someday you are determined that, okay, now I'm going to take the plunge, you can also get in touch with me, or, you know, otherwise, you know, you can do some Google search and you will definitely find opportunities. I can bet that there are many interesting opportunities as long as your interest and passion is there. Okay.
Thank you.
Can I just add just a small example in terms of you know, correlation between higher education and what you can achieve? You know, you should go to Ludhiana and you should see the kind of things they churn out there, you know, in terms of machine tool industry and products and whatnot. And they will all be not even SLC, not even school going kids. So that way, what Professor Parag is saying is very important. As long as you have the passion to pursue and your risk-taking ability, you can actually really do wonders. Just to have that engineering attitude. Mujhe hoga. That attitude is very important.
That's right.
And that is what is going to take you forward. And see, of course, I'm not trying to say education is not important, but you can innovate, you can do a lot of engineering stuff. No, I again have one senior friend, colleague in the industry who runs a stainless steel, business. You know, he makes many products, kitchen utensils and variations of that. And he's not even undergraduate, you know. But the kind of wealth generation he's doing, you know, of course, he's a Gujarati, and I don't have to tell you about their business, their mind. So he just wants to keep innovating, and he keeps participating in every sheet metal conference I organize. He says, Saab, every conference I come to a conference, I have something to take home from the conference. But it's not like he's a highly educated person or anything. So education is important. This is not to say education is not important. But what is even more important could be that engineering aptitude, engineering attitude, which Parag also emphasized. If we have all that, then, you know, we can really be a big innovator and we can achieve a lot of stuff. And that's a comment I want to add, which anyway Parag had already hinted upon significantly. Yeah, thank you.
Sir. Okay, sir. Thank you for the inspiring words and the guidelines. Now we have already late and the scheduled time, so I'm directly rushing to the vote of thanks session. So I invite Mr. Mevin T. Kurula, Assistant Professor, to propose the vote of thanks.
Thank you, Marin. Am I audible?
Yes.
Yeah. Yes.
Okay. Good evening, all. I would like to thank our distinguished speakers, Professor K. Narasimhan and Professor Parag Bhargava from IIT Bombay for making excellent presentations and making this online seminar interesting and very meaningful. The talk was very informative and the way it was arranged was beautiful. We are really enlightened with your knowledge and presence. Especially Professor told about the various innovations by metallurgical students in IIT Bombay, Kanpur and Kharagpur, which has created great enthusiasm in us. I am sure that the participants, especially the students doing graduation and also those who are engineering aspirants, are highly benefited from this session. On behalf of Department of MME, I would like to extend our sincere thanks to Professor K. Narasimhan and Professor Parag Bhargava for accepting our invitation to take this session. I also express my sincere gratitude to Mr. Savisaji N for making this session happen. Also, our heartfelt thanks to all the members for your active participation in the midst of this COVID pandemic situation. It was highly encouraging to us. Before winding up today's session, I would like to remind you about our final talk of the webinar series. I'll be sharing the details of the next session. The next session will be taken by Dr. Shivprasad Murugan from Center for Industrial Technology Development, Dongyu University, South Korea, and his topic is Career Prospects for Metallurgical Engineering Graduates in Welding Industry. Existing participants can continue with the remaining talks. The details will be intimated through mail as well as in the Telegram group. New participants may register through the link given in the brochure as well as in our Facebook page. Also, One more thing, the videos of the previous talks are available in our YouTube channel as well as in our Facebook page. Those who have missed the previous talks can go through that. Once again, thank you all.
For the feedback form, you can see the link in the comment box. I request everyone to give a feedback. And with that, we'll keep you posted on our progress and hope to attend the next session on August 10th. And see you soon, everyone. Thank you.
All right. Thank you.
Thank you so much, sir. Thank you so much, sir.
Thank you, sir.
All right. Bye.
Bye, sir.